In this lecture, I'll talk about the normals to planes and the equations for planes. This is for Math 202, Chapter 1. A line is determined by 2 points. Okay, you know that. A plane is determined by 2 lines. Right, so for example, if you have this plane right here, if I have 2 vectors in this plane, 2 lines in this plane, that determines the whole plane. Anytime you have 2 lines, you can put a plane through them. Just like when you have 2 points, you can draw a line through them. Well, how do you get these 2 lines or 2 vectors? You can get them by using 3 points. So the idea often is to have 3 points in the plane, and from that find these 2 lines, and from that find the equation for the plane. Now you might think that a plane, if a line in 3 space requires a vector parametric equation, a plane should require even more, but actually the equation turns out to be simpler. For a plane, we use these normals. This is a normal to the plane. Remember there were 3 terms, all meaning 90-degree angles. One is perpendicular, and you use that for 2 lines. 2 lines are perpendicular. The word orthogonal means the same thing. It's usually applied to vectors. 2 vectors are orthogonal, means they're at right angles. It means their lines to them would be perpendicular. And there's another term, normal, and that also means at right angles. And it's used for a line compared to a plane. So normal is both a verb and a noun. As a noun, it refers to this particular vector that is at right angles to the plane. Normal also refers to the state of being at right angles, okay, between a line, a vector, or a plane. So we have these normals to the plane. As you can see, if you have a plane in space, assume this kind of yellow thing isn't just a little rectangle but goes on forever and ever. So this is representative of part of the plane. You have 2 normals. One would point up and one would point down. Right? Those are both normals. They both are at right angles to the plane. This is an important point. It comes up in mechanical engineering, especially when you're trying to describe surfaces, perhaps to put in a hydrocode or something. You have to be a little careful of what normal you're talking about. And a lot of this is resolved by drawing a picture. Drawing sketches is always a good idea. I just wanted to point this out for later in the semester, later in the class. For a plane that's flat, there is one normal vector. It could be moved around, but there is really, as you know, vectors can move anywhere, but there is only one normal vector, or one direction for the normal, shall I say. Well, there's the one down here. Okay, now I've said everything backwards again, so let me say it again. If you have a flat plane, there is only one normal, either going, on the upward pointing normal or the downward pointing normal for that plane. It's flat. If you checked out vectors here, you would get a vector pointing in the exact same direction as this normal. Might be longer or shorter, but it would have the same direction. When that surface is curved, there are normals at each point. Here's a whole bunch of normals on this curved surface. Each one of these vectors is perpendicular, is normal to the surface at that point. But when you move over here, it's a different vector that is normal to the surface. Just wanted to point that out. It's a difference when a surface is curved than when it's flat. So now I'll go through the exercise of calculating the normals. So you have 3 points in the plane. It could be anywhere. Let's say, better get the pin. Okay, say this is 1 point, and this is another point, and here's another point. So this is P0, P1, and P2. It doesn't matter where the points are as long as they're not collinear. If they're collinear, you'll not get 2 vectors. Remember, the purpose of the 3 points in the plane is to give you the 2 vectors. So let's say these are my 3 points. I can create vectors from P1 to P0. I can create another vector. So this could be V1, let's say, and this is V2. Right. Now to create the normal, I take the cross product of these 2 vectors. If I take V1 cross V2, the way I've drawn this, I will get that normal that's pointing up. If I go V2 cross V1, I'll get the normal that's pointing down. So it just depends on what you want. You just have to be careful with signs and remember the right-hand rule. So here I've worked out the terms. Well, this actually is in 1, but in that diagram, this would be n1, the upward normal, would be v1 cross v2. Work through this, you get a vector. The normal pointing in the other direction, well, that's obviously pointing in the other direction. Okay? And it doesn't matter, v1 and v2 are just arbitrarily assigned. If you have a real problem in mechanical engineering or in some real problem, do your sketch, make your sketch, and make sure that the normal that you are calculating is pointing in the direction that you think it's pointing. You don't need the unit normal to write the equation for the line. But often in many problems you need the unit normal because all you care about isn't the particular length of that normal, which would depend on the length of the vectors in the plane. You only care about the direction. So usually you want the unit normal, and a lot of times people will say normal will mean the unit normal. Of course, to create the unit normal, you create it just like you create any vector. You find the magnitude of the vector and divide the vector by its magnitude, and you get the unit vector. Some people like to write the whole vector like this. I don't do this. But like 6i minus 24j. This is something not to do, bad habit or bad practice. And then divide the whole thing by the square root of 936. Okay, that's really bad practice. That's just not good. All right, and it's very confusing. Oh, the other thing is you don't always have to work out this to like 10 decimal places. If you leave a radical, a lot of times it's okay because often later in the problem that radical will resolve itself. Also, by leaving it in this form, you will remember what you're doing. When I look at this, 6 over square root of 936 minus 24 over square root of 936, 18 over square root of 936, I know immediately what that 936 was. I know it was the magnitude of the vector I had started. Right? And like I said, it's better to write the I as a self-contained component, the J and the K as self-contained components, and not write this where you have a vector all divided by one number. Okay. And of course we could create the unit vector in the other direction according to that. We could put 2's here and 1's here to separate these out. And the normal, the magnitude of each one of these vectors, of course, is equal because we use the same vectors, the same v1 and v2 to create both n1 and n2. So they're your normals, and they're your unit normals for a plane. So the next problem is to take that normal and write the equation for the points in the plane. Not all problems will require this, but if it's required to get the equation for the points in the plane, then you use the normal to do it. And you use the idea of a dot product. If I have some reference point in the plane, P0, some point I know, and P is any point in the plane. It could be over here, 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 it doesn't matter. It's just some arbitrary x, y, and z for a point in the plane. I can create this vector, which I'll call r, and the dot product of the normal and this vector is going to be 0 because the normal is at right angles to the plane. So I use the idea that a dot product will be 0 if the vectors are at right angles, or orthogonal. So these vectors are orthogonal. So that's what I use to create the equation for the points in the plane. So first I'll just do this in general. N dot r, and let's say n has capital A, capital B, and capital C are the components of the normal vector. It does not have to be a unit vector. Okay. Then for r, it will be x minus x naught, y naught, and z naught are the known point in the plane. You have to have one point you know. X, y, and z are then your arbitrary point in the plane. We're going to write the equation for that arbitrary point in the plane. Take the dot product and rearrange. This will be a number because the ABCs are known and the x naught, y naught, and z naught are known. And here it is for this particular case using the same equation, but instead of ABC, of course we had 6 minus 24, and C was supposed to be 18, didn't get changed. Okay, this was 18. All right, and then the point for reference, and you could use any reference point, you'll get the same thing actually, is 1, 2, 3. So here, write that down. So the reference point, x naught, y naught, z naught, this is just from the example I'm working through here, but of course you'll have your own, was 1, 2, 3. And you see those appearing right here. Here's the 1, here's the 2, here's the 3. Take the dot product, work out the terms, put the constant all the way over on this side. It happens in this case to be 0. There's your equation for the points in the plane. If you use the other normal, you would just have different signs here, which could be resolved and give you exactly the same. So it really doesn't matter which one you use. When equals 0, and of course you could multiply through by -1 and get the same equation. Now sometimes you're given the equation for the points in the plane. For example, in 10 in the homework 1b, here are the equations for 3 planes. So the question is, can you back out of this what the normal is? Well, remember that, okay, I'll go back to the other slide for a minute. Well, here I brought the other slide forward. So you can see, here's your ABC on this side multiplying x, y, and z. What is on this side is just a constant. It had to do with your reference point and the values of a, b, and c. So when I look at this equation, I could see that for this case, a is 3, b is 3, and c is -4. So the normal to this plane, for plane 1, is 3i plus 3j minus 4k. And for plane number 3, the a is 6, the b is -2, and the c is 3. So from those equations for the plane, you can easily find, you can just read off the components for the normals and then create the normal to the plane by using, assigning them to ijk's. And now if you want to determine if 2 planes are perpendicular or 2 planes are parallel, all you work with are the normals. It does not have to be the unit normal. You just have to work with the normals. If 2 planes are parallel, the unit vectors are perpendicular to the planes, so the unit normals are also parallel. So if 2 planes are parallel, so if 2 planes are parallel, then their 2 normals are parallel. That would mean n for the first plane cross n of the second plane would be 0. 2 vectors that are parallel have a cross product that's 0. What happens if the planes are perpendicular? If the planes are perpendicular, then the normals are perpendicular, and you can use the dot product here. And that will be 0. So instead of worrying about the planes to determine whether the planes are perpendicular or parallel, all you have to do is look for the same, look at the normals and determine if they are parallel or perpendicular.